Hi everybody, this is David Paul. So we're here for the next few minutes to talk about how to effectively clean RO units. I'll have about a 40-minute presentation, and then there should be plenty of time for question and answers. Just type your questions into the questions box. So as we're talking about chemical cleaning really is site-specific because each foulant and scalant is site-specific, even time-specific. We have had clients where 1 year we did a cleaning study and a cleaning evaluation, and it turned out that certain chemicals and certain procedures worked best, and then the next year came back and it was totally different. So even when you have a specific foulant and scalant, sometimes that's going to change over time. Just depends on your feed water and your operation. So I can only really, in this brief period of time, cover general features of a good chemical cleaning. And you can, at the end, talk about additional chemical cleaning training that we have, or you can experiment at your own facility. So this presentation is recorded, and it'll be available at this website address. You don't need to write that down because we're going to send you a thank you email tomorrow, and there'll be a PDF of this presentation, so that URL will be in the presentation. So as far as the agenda, I'll just spend a couple of minutes introducing myself, and then we'll talk about why RO units scale and foul, when to chemically clean, features of a good chemical cleaning, and how to evaluate the results of chemical cleaning. And then that'll be followed by the question and answer period. So I've been in RO water treatment for longer than most people in water treatment today have been around, since 1977. I started at a power plant, and I started as an operator, and just happened to walk into a plant that had this newfangled thing, reverse osmosis, but it was all on industrial wastewater, so all the waste from an 1,800 megawatt coal-fired power plant. So we had lots and lots of problems. Ended up the first RO system had to be completely demolished because the pretreatment system didn't work. But then the new system had this new membrane, polyamide. It wasn't today's polyamide thin film composite, but a asymmetric polyamide. But just like today's PA thin film composites, you can't chlorinate it. And because of that, we ended up with lots and lots of biofouling and having to chemically clean every RO unit at least once, sometimes twice a week. So I was an operator for 2.5 years, then a shift supervisor for 1 year, then the manager of those facilities for 8 years. And then 27 years ago started David H. Paul Inc. So we do training, we do consulting, and we provide technical service like membrane element autopsies, and also we provide chemical cleaning evaluations for clients where we find the best cleaners and cleaning procedures for removing a particular problem. So let's talk about why RO units scale and or foul. We'll start with scaling first. And here's the definition that we use. This is not going to be a standard definition anywhere that you look in a dictionary and you find this definition. But we consider scaling as something that occurs with dissolved substances like calcium and carbonate ions that are independent of each other, and then due to concentration within the RO unit, we force those ions closer and closer together until they finally achieve 100% saturation, and that's all the water will hold. And we won't talk anything about supersaturation. So that's our definition of scaling. Here's a picture of scaling on the outside of a membrane element on the left, and on the surface of the membrane when the feed spacer has been removed. So we see that we have crystals that are in the feed channel or the feed spacer as well. So when we're talking about scaling, we're talking about ions, cations being positive ions and anions being negatively charged ions. And these, the single charged ions are not going to give us a problem because they can get so close together that in an RO unit we're never going to scale with single charged ions. They will dissolve sometimes even hundreds of thousands of milligrams per liter. We're going to have a problem with the double charged ones, the double charged cations and the double charged anions. There's a certain distance that they can get between each other where they're equally as attracted to each other as they are to other things in the water, and that's called 100% saturation. If we get them any closer than that, then some of them are going to have to leave, and that's called scaling. So here's just a graphic of an RO unit. The rectangle is the actual RO unit, or the representation of the RO unit. This line is a representation of all of the membrane that's in the RO unit. We take a pre-treated feed water, send it to a high pressure pump, we pressurize it, and then due to the net driving pressure that we supply, we're going to force a lot of water molecules to go through the membrane. And we call that permeate when it goes through the membrane. The dissolved substances can't go through, at least not very readily. So that means the water molecules go through, the dissolved substances don't. So we concentrate every inch or centimeter of the way, from the first inch or centimeter to the last inch or centimeter. So we're concentrating that feed water. So every inch or centimeter of the way, the scaling potential is going to increase. So based on that, based on scaling being due to concentration, which one of these elements would be most likely to scale? Well, if you said the last one, then you would be correct, because the last one has the most concentrated feed water. Wherever scaling occurs, we're going to have scaling from that point on, because we're going to be at or exceeding 100% saturation from that point on. Okay, so that's just a quick overview of scaling. Now let's take a look at fouling. So here again is our definition, not a universal standardized definition. So here for fouling, we're talking about particles, living or non-living particles. So living particles, mainly bacteria. Non-living particles can be anything from silt, sand, clay, precipitates like iron, rust, things like that. So either the particles come in and don't leave, so they don't go out in the concentrate, they get stuck somewhere, or we also consider fouling organic polymeric types of materials, oils, greases, polymers, anything that can come in and doesn't leave. So it sticks to the membrane, sticks to feed water spacer. So we call that fouling. So on the left, there's a picture of fouling on the surface of the membrane. And in this case, the feed spacer has been removed. And here is fouling showing that it's plugging up the feed spacer. So the feed spacer would be laying on top of the membrane. So this is absolutely critical. In this short webinar, we can't spend a lot of time on it, but there are two things that control the fouling rate of any membrane system. This is true whether we're talking microfiltration, ultrafiltration, nanofiltration, or reverse osmosis. The single biggest parameter that controls the fouling rate of an RO membrane system is called water flux. The second is Crossflow, but notice that I've made the font significantly smaller. So number one is going to be water flux. So water flux is the amount of permeate that passes through a given area of membrane in a given amount of time. So in American units, we use GFD, gallons of permeate per square foot of membrane per day. So the higher the GFD, the higher the fouling rate. In metric units, we use LMH, and that's liters of permeate per square meter of membrane per hour. So again, if the LMH is higher, the fouling rate will be higher. So here's just an illustration of a 4-pressure vessel stage of an RO unit. And we see here that each RO membrane element, here's American units, here's metric units, each element in series makes less permeate. Because it makes less permeate, that means that the GFD is lower. So in the pressure vessel, the GFD is highest in the first inch or centimeter and lowest in the last inch or centimeter. Well, water flux, again, permeate flow per given area of membrane per given amount of time, is the main controller of your fouling rate. Since GFD is the highest here, then it means that that's going to be your highest fouling rate. The second parameter that controls your fouling rate is called crossflow. Crossflow is the flow rate tangential to the membrane. So this is the flow rate that scours or cleans off the membrane, removes the dissolved substances. But right at the surface of the membrane, water has to take a turn. So you don't have crossflow right at the surface of the membrane. This is called the boundary layer. In the boundary layer, you get dissolved substances that concentrate, but dissolved substances can diffuse out. Diffusion is random motion from areas of higher concentration to areas of lower concentration. The suspended particles, living and non-living, like silts and clays and bacteria, colloidal silicas, anything that particulate in nature, that can be deposited on the membrane. The permeate drag, the water molecules here will tend to hold them down onto the membrane. So again, this is what we're calling fouling, if it's especially if it's serious enough to cause us to have to chemical clean and to spend a lot of time and money in trying to correct this. All right, so again, cross flow rate is the feed concentrate flow rate. Well, the higher the feed concentrate flow rate, the smaller the boundary layer, because the shear force of the higher feed concentrate flow rate is higher. So that means that your dissolved substances don't concentrate as much and your suspended particles can't stay on the membrane as easily because they have this high shear force. So when we're talking about fouling, which element is the highest fouling? All right, so if you said number 1, then you are correct. And again, that's mainly because of GFD. So when you have a problem in the first stage, the chances are we're talking about fouling. If we have the problem mainly or only in the second stage, then the first thing we'll think of is scaling. It's not always, but more times than not. All right, so we've talked basically about how we scale and foul. We scale due to concentration, and we inject scale inhibitors to keep us from scaling, or we have water softeners up front to keep us from scaling. So as long as we keep an RO unit at the proper recovery rate and we're in our softeners operating properly, and or I shouldn't say and or our scale inhibitor injection is operating properly, then scaling shouldn't be a problem. So when we do scale, it usually means that there's been some upset, or we're at a higher recovery than we really think we are, or the feed water has changed, and then we scale it and it'll be time to clean. For fouling, fouling can occur continuously especially on surface waters. Fouling on a nice deep well water usually isn't a problem. But when we do foul and we see that the feed pressure is going up and the pressure drop across the first stage is going up, then it's going to be time to clean. Well, When do you decide when it's time to clean? That's what we're going to talk about in this section. We don't want to wait too long to clean. That's really the kiss of death for most foulants. Not so much for scalants, but for foulants. So what happens, this would be a first element. This would be the first element in the first stage. Here's the feed side. Here would be the concentrate of this unrolled 8-inch membrane element. Well, you can see here that there's dead zones. There is no water, zero water going through these areas. So this element is said to be channeled. So because of that, this is going to make our cleaning very, very difficult, especially if you're just using a standard cleaning procedure that says something like mix up your chemicals, get the temperature right, get everything dissolved, then circulate for an hour, soak for an hour, circulate for an hour, rinse, and you're done. Well, that might work if you clean at an early stage. But if you clean at the point where it's channeled, then there's no way, because your cleaning solution is going to take the same path as was taken during normal service. It's going to take the path of least resistance, which is not going to be in the plugged areas. So it could take hours and hours and hours and even days of soaking and circulating to be able to get this clean back to near new performance. So again, we don't want to wait too long to clean, and I'm going to tell you what we think you should look at in order to determine when to clean. And that is when the normalized permeate flow drops 10 to 15%. We don't have time in this webinar to go over that, but we have lots of training programs if you need to know about normalized permeate flow. So the normalized permeate flow drops 10 to 15%, or the pressure drop across any stage increases 15 to 25%. This is fairly conservative. So if you clean at this early stage, you may be able to easily get an RO unit cleaned back to new or near new performance in just 3 or 4 hours of cleaning. If you wait until the pressure drop doubles, then chances are you've got channeling, and your chemical cleaning is not going to be getting you back to new or near new performance in 3 or 4 hours of cleaning. And we want you to clean whichever one of those comes first. Normalized permeate flow drops 10 to 15%, or the pressure drop across any stage increases by no more than 25%. All right, let's go over some just general information on chemical cleaning. So we're cleaning to remove scalants and foulants. One of the problems that RO units can experience, which is membrane damage, is not amenable to chemical cleaning. So we're only going to be talking about cleaning scalants and foulants. So just I want to do the common sense version of how to remove scalants. Because of the boundary layer, you will always scale the membrane, because at the surface of the membrane is the most concentrated water. So occasionally you'll actually have scale that's only on the surface of the membrane. In this case, there is so much scale buildup that it's actually gone into the feed channel, and that's why we're seeing all this crystalline material. But it's not just this crystalline material that has to be removed. We also have to remove the scalant from the surface of the membrane. There are two general categories of cations of scales. Cations and anions are 99%. And polymeric silica is the other area. So when we're talking about cations and anions, we're talking about double-charged cations like calcium and double-charged anions like carbonate. So the calcium +2, carbonate -2. When they reach a certain concentration, they hit 100% saturation. If we concentrate them more than that, then we're going to scale unless we have done something in pretreatment to keep us from scaling. So again, softening or acid injection or scale inhibitor injection. the most common scale on the planet is calcium carbonate, and that's true whether we're talking brackish water, fresh water, seawater, whether we're talking surface water or well water. It's because 4% of the Earth's crust is calcium, so our waters all come into contact with calcium, and the carbonate is coming from CO2. And we all know that about CO2 in the atmosphere. So we have CO2 that's in the atmosphere, but most of that CO2 in the atmosphere dissolves in our surface water. So we're 70% covered with water. So the CO2 dissolves in water, and then we'll see here in just a few seconds, we'll see the relationship between pH and CO2. So the carbonate came from CO2 because the pH was above 5.5. So all we have to do is drop the pH down, and we're going to turn that carbonate back into CO2, in which case we're going to see a lot of tiny, tiny little bubbles in our cleaning tank. So calcium carbonate is the most common scale. Fortunately, it's going to be the easiest one to remove, so long as we can get cleaning solution to go through it. Just had a client just last week that had to throw away elements because they were so plugged up they couldn't get any cleaning solution to go in. Now, they removed it and replaced them, but the elements are still around. We're going to see if we can soak them and get them dissolved, because carbonate is going to dissolve readily when we put it into contact with acid. But that's going to be the only easy one. And again, it's this relationship. So this is the relationship between CO2 below a pH of about 5. All of your CO2 is in dissolved CO2 form, which you can call carbonic acid. Well, as the pH goes up, when it gets to the neutral range, here's where most of our natural waters are. The pH has converted most of the CO2 into bicarbonate ion, but that's a single charged ion. That's not a problem for us. But even down here, we have parts per quadrillion, then parts per trillion, then parts per billion, then parts per million of CO3, of the carbonate. This is the bad guy. This is the guy that can tie up with calcium and form calcium carbonate scale. So somewhere usually in the 7 to 8 pH range, we have concentrated in an RO unit our calcium and carbonates enough that we would scale it unless we have adequate pretreatment. So to get rid of calcium carbonate, we want a low pH. So hydrochloric acid is certainly a way to do that. Citric acid is another one, or citric acid and a little hydrochloric acid. Hydrochloric acid strictly lowers the pH, turns your carbonate into CO2, and you get a bunch of bubbles. Citric acid is going to have a lower pH, so it's also going to off-gas CO2, but it's a chelating agent which plucks out calciums out of the crystal matrix as well. So it does two things, and it's not as dangerous to work with as the hydrochloric acid. And then there are many, many proprietary chemicals out there that can be used. And I don't consider the bulk chemicals better or worse. They both have their pros and cons. All of the other scales, fortunately, are not going to be as common, but also they're not going to be as easily removed, because now we have to chemically dissolve that bond between the calcium and sulfate, that bond that's in the crystal matrix. So with this, a chelating agent, you can also use hydrochloric acid, so that is an option here. And there are other ones. I'm just giving you the top 2 or 3 in each category. So calcium sulfate, something like citric acid, and then proprietary. So every RO chemical cleaning vendor is going to have a menu, and they'll recommend which product for which particular type of scale. So once you have a feed water analysis, you can then calculate based on your RO unit you can calculate what kind of scales you're likely to see. And then finally on scales, polymeric silica, not as common, and I've never seen it on a surface water, but on certain well waters that are high in silica, you can get polymerization of silica, and this takes then a different type of cleaning to depolymerize the polymeric silica. So this is going to be the only scale ordinarily where we're using a high pH or proprietary cleaner, and that's for the polymeric silica. So in general terms, we just have to get the right cleaner. We have to clean at an early enough stage to where we can make sure that we can get the cleaning solution to go in, and then the right cleaner, and then a high temperature, and then it's just going to take time. How long is it going to take to dissolve all of this scalant off of the membrane? So an important factor to remember when I talk about high temperature, the reason that you want high temperature is for every 10 degrees C increase in temperature, chemical reaction rates double. So that means that if you'll raise 18 degrees Fahrenheit or 10 C, you raise the temperature, then you're going to get twice the cleaning in the same amount of time. Or you can get the same amount of cleaning in half the time. So it really is advantageous to go to a relatively high temperature. But you need to be sure that you have the information from your membrane manufacturer about temperature versus pH. Do not use specification sheets for this. The specification sheet for your membrane element may say that you can go to a temperature of 113 Fahrenheit, 45 C. And then somewhere else on the specification sheet, it says you can operate this RO unit at 1 to 12 pH, and you can clean it at 1 to 13. Well, that's on a specification sheet. That's not what you're supposed to do at the same time. You don't go to the highest temperature and the highest pH. That's quite aggressive. And chemical cleaning does take off life off the membrane. The more aggressive the cleaning, then the more life. So here's just an example. This is actually a Dow example where they'll tell you that there are different types of RO membrane, that if you want to go to the highest temperature, you're going to have to limit the high pH to 10.5. If you want to go to the highest pH, fine, but you're going to have to limit the cleaning solution temperature to much lower. And then here for nanofiltration products. So every membrane manufacturer is going to give you some guidance on temperature versus pH. But just remember, don't get more aggressive than you have to. So find out from your membrane manufacturer what you can do. Then removing foulants. Again, we're looking at surface foulants and feedwater foulants. 3 general categories are the most common: organics, bio, and silica. Now, some of you may have iron fouling. You may have other types of particulate or organic types of or inorganic types of fouling. But these certainly we see the most, and organic and bio probably the most. So first stage organic bio problems. So if we look at solubility, that's what will dissolve. The solubility of organics dissolve at a high pH, which anyone who's dripped caustic on their skin knows, because your skin dissolves with the caustic. Whereas organics precipitate at a low pH. So because of that, we want to clean at a high pH. So caustic, also detergents can be very beneficial. Detergents being like surface wetting agents. And just like if we try to clean engine oil off our hands, we go just to the sink and run water. It's not going to do any good because the water and the oil don't mix. But we use a detergent that has a non-polar end that dissolves in the oil and a polar end that dissolves in the water, then we can get this off. And a lot of these organics and biofilm formations can have a significant amount of non-polar components, so that detergents can be very beneficial. And like I said, there's always a great variety of proprietary products that are out there. Bio is essentially organic. So the cytoplasmic membrane and cell wall around a bacterium is all organic, so it's the same type of thing. We can use caustic detergents and proprietary cleaners for that. Then silica particles, if we actually want to dissolve them, then we'll see that the minimum solubility of silica is like a pH of 7 range, 7 to 8 range. Silica gets a little more soluble at a lower pH, but a lot more soluble at a high pH. So again, this is going to be the one time that we're going to be using a high pH cleaner like caustic to remove silica. As far as a general procedure, we need to use the right cleaner. So if we're doing silica organics or bio, we're using a high pH cleaner. A high temperature, again, chemical reactions, rates increase, plus with biofilms, this may loosen them up, thin them out. Just like if you've got steak, you've had steak the night before and the plate with the fats that were dissolved because they were hot, you know, the next morning they're cold. Well, by heating that up, then we can get it thinned out to maybe where we can push that out. The difference, one of the main differences between scaling removal and foulant removal is we really would like a high flow rate, because we're not going to be able to dissolve all of these foulants. The membrane itself is organic, the foulant's organic, so trying to find something that will dissolve the fouling layer and not dissolve the membrane can be a challenge. So we are going to have to use some turbulence, some high flow rate. In measuring the cleaning effectiveness, you're not going to really know how effective you've been for at least 24 to 48 hours. So even though you look at your tank and your cleaning tank is nasty, it's got all this material, and say, whoa, we really cleaned the heck out of this RO membrane. What really determines it is when you check your normalized permeate flow and your pressure drops after a day or two. Sometimes, especially if you just use high pH cleaners, you may find that it takes a day or two for the membrane to stabilize. So it actually gets better and better as you go along 24 to 48 hours. So we're going to always recommend that you're monitoring, that you're trending. So in this case, we're seeing that the normalized permeate flow dropped. We did a cleaning. Well, how well did we clean? Well, it looks like we cleaned about 50%. So we cleaned a lot off, but we still are not back to new or near new performance. So if we continue to operate like this, we're probably making the decision for a lot more cleaning and shortened membrane life. So in this case, based upon this, we would like to do another cleaning and see if we can get this back to new performance. All right, so that basically takes us to the conclusion here. So we've gone over, you know, why RO units scale and foul, when to chemical clean, features of a good chemical cleaning, and how to evaluate the results of chemical cleaning. So we are going to have a 3-day, it's a new hands-on seminar that we've got February 9th through 11th. So, you know, we're dealing 40 minutes in this webinar where we have 3 days and it's hands-on. So we're going to do lots of hands-on cleaning exercises, and it's going to be a lot of fun. And it's going to be held at American Water Chemicals. You may know them also as Alkema. and they have lots of good equipment, and they do membrane element cleaning there for clients. So we're going to have lots of equipment, and we're going to be able to do some real unique things that you won't be able to do without some modifications at your plant. So if you can make that or are interested, let us know. Okay, with that, then it's time for question and answer. Okay, so if you have a question, please go ahead and write the questions in the question box. So question 1, are there any positive effects of a backflush with permeate, both for spiral wound and hollow fiber? Well, I'll start out with the hollow fiber because that really is the backwash. So yes, I mean that's usually the way of cleaning a hollow fiber. And when I'm saying that, a hollow fiber microfiltration or ultrafiltration, if you were somebody that actually had hollow fiber RO, then no. But that's not common. So I don't know who's asking the question. But hollow fiber RO, you do not go from the permeate to the feed, and you don't do that with spiral wound as well. So whenever somebody says a backflush of permeate, I always have to ask the question, are you talking about permeate going from concentrate to feed, or just cleaning solution from concentrate to feed, or are you talking about going from permeate to feed? So with this question, I'm sure we're talking about going from permeate to feed. Because of the membrane's construction, it is not advisable to ever go from permeate to feed with pressure. So you're pressurizing the permeate side and forcing water molecules through. Because the way the envelopes or leaves inside the membrane element are constructed, they're constructed for water to go from the outside to the inside of the leaves, not the other way around. We call that permeate back pressure damage. So if you ever have more than, say, 5 psi or 10 psi of pressure on the permeate side versus the feed side, then chances are you're going to damage the membrane. And if you get to 15 psi more pressure on the permeate side than the feed side, it's a given that you're going to damage the membrane. Okay. What is the problem with a makeup water that is very high in chlorine? Well, the membrane itself is oxidized. So oxidizing agents like chlorine want to take electrons. Well, they can take electrons, especially from the nitrogen-carbon bonds that are in the RO membrane. So this actually would damage the membrane. So whether we're talking about feed water or we're talking about cleaning solutions, we don't want any chlorine in the feed water. I have several ROs, and the carbon fibers are, and the carbon filters are only removing half. What is the problems that I can expect from this? So I'm assuming we're talking about activated carbon filters upstream of the RO unit, and the filters are only removing half of the total chlorine residual. So with this, your membrane, your RO membranes can withstand a certain amount of chlorine attack. Most manufacturers will say somewhere between 1,000 to 2,000 ppm hours. So that'd be 1,000 ppm for 1 hour, or a tenth of a ppm for 10,000 hours. So it's just due to that dosage. So if your activated carbon filters are only removing half, then either you've got channeling going on, or you've used up the life of the activated carbon. You need new activated carbon. Or I've also seen where a bypass valve was opened, where you've got water going around the activated carbon that is not dechlorinated. So this needs to be fixed because it can cause damage. How to effectively clean membrane fouled with aluminum and manganese. I've only run into the aluminum. I have not personally run into the manganese. I would use on that one, I would use a proprietary cleaner that's specific to either aluminum or manganese. The aluminum usually is only seen in city water because that's usually the source of the aluminum is aluminum sulfate fed in city water. Manganese is almost always going to be a well water source. So I would recommend proprietaries for both of those. Do you find adding sodium lauryl sulfate in addition to EDTA on a high pH clean effective for removing foulant? Yes, with and without EDTA. The sodium lauryl sulfate, I've seen some really nasty waters, organics, that was just about the best thing that would take it out. I came in a bit late. If a high pH solution is being used in the RO cells, is there any need to isolate, recalibrate the ORP sensor? Not that I'm aware of, but I actually have never looked into that. So you'd have to ask somebody else on that one. I've not seen the problem. Can you give some guidelines on flow rate values to be maintained for cleaning foulants and scalants? I'll try to do it in 1 minute. We recommend that you start out low flow, like 10 gallons a minute per 8-inch pressure vessel, divide by 4 4-inch pressure vessels, and do that for 5 to 15 minutes, and then go up to 20 gallons a minute per 8-inch pressure vessel for 5 to 15 minutes, and then if you can, go to 30 gallons a minute. We've just seen a few times where if we hit a foulant too fast right at the beginning, that it takes it off the surface of the membrane and slams it onto the feed spacer, so you end up having a higher pressure drop after the cleaning than you did before. Can you, okay. Is it possible to reuse the chemical from second stage into third stage if you are removing silica? It's, yes, it's possible. You would, depending on whether you're using proprietary or not, if you're using bulk chemicals, you're more likely to be willing to dump the tank and make a new charge. Because one thing that happens when you're cleaning these materials off is that your cleaning solution can become saturated in time. So if you're using just caustic and you're cleaning off organics, well, at some point you may not be able to clean any more organics off because you're basically saturated in the organics, in which case if you dump it and make a new tank and the cleaning resumes in a beneficial manner, then you're in good shape. So yes, you can do it, but just monitor to make sure that your cleaning solution is still doing something. There's still some cleaner in there that's going to help you out. If there's only one stage RO, how does one determine if an RO unit is fouled or scaled? I think that's an excellent question, because now we don't have the location. We just know that somewhere in the one stage we've got a problem. Fortunately, I mean, most one stage systems are seawater systems. As long as you know that you have your scale inhibitor is being injected and there isn't a scale inhibitor problem, such as your scale inhibitor has been biodegraded, so in a day tank, if you pump it full strength, then you'll never see that problem. But if you dilute scale inhibitor, then bacteria can grow and consume it. So I think what you would probably do there is you'd look at your cartridge filters, you'd see about particulate material, open up the front and back of a pressure vessel, look in, see what you see, smell it, see if you're smelling bio, then chances are it's that, but especially on a seawater RO system, scaling is much less likely. What is the right order to start a chemical cleaning? Our standard is if it's a first stage problem, we're going to clean with a high pH first or only. If we think it's organic, we think it's bio, then that's what we're going to do. We're just going to clean for that problem. If it's a second stage and we think it's scaling, then we'll just clean for the scale. Now, I know a lot of you have SOPs, standard operating procedures, or cleaning procedures that say always do one and the other. You may have a procedure that says clean the whole RO unit. We typically don't clean except where the problem is. So we don't typically just clean the whole RO unit, and sometimes we do the high pH cleaner and followed by a low pH cleaner just to stabilize the membrane quicker. Is it possible for foulants to reprecipitate on the membrane when doing an overnight soak? Well, it certainly can lay out. When you're talking foulants, you're talking suspended particles. So yes, they can do that, and but when you have the turbulence in the morning, you know, it may take it out. I think you're gonna have to find out for yourself on that. If your pressure drop was higher in the morning than it was the night before, and the pressure drop does not improve after you start it up and you've got your turbulence going again, then I would say yes. Your answer would be yes. Does increased cleaning frequency decrease lifespan of seawater RO membranes? Yes, as well as brackish water RO membrane. If the RO maker, so a manufacturer, suggests pH 12 maximum at 25 C, could we use pH 12.5 at 20 C? This one you need to find out from the membrane manufacturer. That's the only way that you can really tell what's going to be allowable for your membrane. Another question, should cartridge filters be changed in between CIP if DP doesn't indicate they should be changed? So in other words, you know, typically we change cartridge filters 10-15 PSI, so you do a chemical cleaning and it's fine. Yes, you can reuse them. My only recommendation is be sure that you've dried it. Don't allow those cartridge filters just to lay up in even high humidity, even if you just drain it. If you're not going to come back and use that cleaning skid for a few weeks or more, then you should take them out and let them air dry. Okay, what do you think about sodium chloride cleaning solutions? Maybe referring to the patented process, direct osmosis high salinity. We have experience with that. For chemical cleaning, when you have enough osmotic pressure, osmotic back pressure, like if you have a 1% cleaning solution, 1% is 10,000 milligrams per liter. So you have roughly, it's not going to be exact, but ballpark 100 psi of osmosis back pressure, osmotic back pressure. So if you're cleaning at 60 psi, then you shouldn't make any permeate. That's advantageous because when you're making permeate, you have the permeate drag. So you have permeate molecules that are holding down the foulant onto your membrane. So you could do caustic, and if you're making permeate and you wanted to stop making permeate, you can put a little sodium chloride in there, and that would give you enough osmotic back pressure so that you wouldn't be making permeate, unless you have O-ring leaks, in which case you have to fix the O-ring leaks. Any comment on how much clean degrades a membrane? How many cleans a membrane can tolerate? We have some rough guidelines based on experience over the years that if you're cleaning once a week in an industrial setting, you're probably looking at 1 to 2 years of life. If you don't have to clean more than 6 times a year, then you're probably looking at 3 years plus. And in some industries, if you're not cleaning at all, you've got a beautiful well water, and that's the only time we usually see that is on a well water source. You know, you can get more years than 5. Okay, we have seawater RO, and the feed seawater is taken from a district cooling seawater facility. This feed water is chlorinated, and we dechlorinate before feeding to the seawater RO. It is not a good idea to use pre-chlorinated seawater, as even after dechlorination, such water will biofoul the membrane. As we are forced to take chlorinated water, is there any way to minimize the biofouling of the seawater? That is a huge problem in the industry. I consider it the biggest, overall the biggest problem with RO membrane water treatment, and that is chlorination, dechlorination. The active chlorination takes organic molecules that bacteria can't eat and turns it into molecules that it can eat, called assimilable organic carbon. So it's a huge problem, and I can't give you anything other than the most expensive, but something that will work would be biocide injection periodically into the RO unit. You may be able to get away with some operational changes, but it's not common. I mean, this is a big problem, and it's one that you'll need to spend some time on. What micron cleaning filters do you recommend? I'm fine with 5 micron. Scale inhibitor can grow bio and or degrade? Yes. Dilute, not full strength, but dilute. Scale inhibitor, we've done a couple of research projects where we did a biocount all around a water treatment system, and the scale inhibitor tank had absolutely the highest number of bacteria. But that's only in dilute. If you're pumping full strength, you don't have to worry about it. What would you say is the maximum time to go in between cleanings if you have a good makeup supply? Our motto is, if it's not broken, don't fix it. So if you never clean, if you go for 5 years and don't have to clean, and you're monitoring normalized permeate flow, and you're monitoring pressure drop, so that means that you have not hit 15% drop in normalized permeate flow, you haven't hit 25% increase in pressure drop across any stage, then don't clean, ever. It's just, there's no need to. It works just fine. All right, so I want to thank you so much. Let me just flip to this next slide, and we'll finish up. So thank you so much for spending an hour of your life here. We always appreciate it. And if you wouldn't mind, if you'd answer our polling questions, which gives us information on what you thought of today's webinar. So it really does not take any time at all. So thank you, and look forward to talking with you again. Bye-bye.